Good afternoon, this is Schweitzer, and we're going to start looking at a little more of a mathematical approach to energy transfer. Typically speaking, if you're in class, we're going to be doing this particular experiment right here. We're going to be heating a block of water in water like so, and it's going to start to boil. So class experiment says the block is heated for a very long time. Since the water will not exceed 100 degrees, the block will gain energy until the block becomes 100 degrees. So if the block, again, remember, energy transfers based on temperature. So if we have a block and the water is, 100 degrees Celsius, and we drop in a block that is, less than that, like room temperature, 20 degrees, you drop it in, then energy will enter the block until it becomes the same temperature, and then no more. So we heat this block up as a means to get our block to 100 degrees. So we take the block out, then we have ourselves a block that is 100 degrees Celsius, just FYI. Okay, energy transfer. Okay, so then what we're going to do is take that block, we're going to drop it into a beaker of water. Okay, and at this point we can wait. We know the block has these things. So the mass of the block, let's go with typically about 125 grams. The water, let's go 125 grams. All right. So we'll do this where they're both the same mass. You just need enough water in here that you can submerge this thing. You wouldn't want it poking out. Temperature initial of the block is 100 degrees Celsius. The temperature of the water typically would be about, let's go 23 degrees Celsius. All right, and we start heat, as the block drops in, it's radiating energy until they both become the same temperature. So you drop a thermometer in here, and you start measuring out your temperatures. We'll have a student do this, okay? And the block will have a pretty big drop off, but the water only picks up a little bit, okay? So let's say at the end, measured out, water will go up to about 27 degrees, and the temperature drops to 27 degrees. So here we go. The water is going to give off energy. Okay. This guy's got a 4-degree change. This guy's got a change that is what? 75 would be a 25, so 73 degrees. Okay. So 73 degrees change as opposed to 4 degrees change. Take a moment, look at these questions down below here. Which ones are true, which ones are false? What do you think? All right. So in hypothesis, the energy lost by the block will be gained by the water. So did they gain the same amount of energy? That's true. Okay, this is true. This is justified. So you might say all or all energy lost by the block will equal the energy gained by the water. Yes. Okay, however you want to phrase it. Yes. Energy didn't go anywhere. We know we have this vast difference change in temperature, but the energy is equal. All right. The temperature will change between the water and the block will be equal only if the mass of the water and the block are equal. Well, we had the same mass, okay, and with the same energy, but we got different temperatures. So this is a no. Okay, so there's more than those factors. So we have equal mass. Okay, we have equal energy, yet we still don't have equal change in temperature. In fact, that is not equal, it's very different. All right, so an energy, as an atom gains and loses energy, how is this temperature affected? Okay, so what are the factors? We got mass, as we mentioned in earlier videos. We have temperature change. And finally, we have, so I'm going to go change in temperature is how we usually do it. And that would be temperature final minus temperature initial. And our last one is the C, or the specific heat, which I alluded to in the previous video. Specific heat. Okay, so the specific heat is the quantum of energy needed to raise one. This is very important. You want to jot this down. I'd put this right here. Okay, so heat is the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. Okay, so the specific heat of water is 4.18 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. Okay, with that being said, keep in mind 1 calorie is equal to the amount of energy needed to raise 1 gram of water 1 degree Celsius. So the specific heat of water in calories, which would be specific heat little c, is 1 calorie per gram per degree Celsius. But then 4.18 joules is equal to calories. So if I multiply this times 4.18, we get the specific heat of water is 4.8 joules of energy per gram per degree Celsius. These are the two specific heats of water depending on the units using. All right, so let's take a moment now, and it says, so we have, let's actually calculate out the specific heat of our block. Okay, have all this information we'll use from the previous slide. Okay, and let's see what we got here. So we have the mass of the block was 125, mass of water is 125. The specific heat of water was 4.18. Temperature initial was 23, wasn't it? What did I do? 23 to 27. Okay. 23 to, and then it went up to 27. So for 3 degrees difference, 4 degrees difference. And then this guy went from 100 down to 27, which was 73 degrees difference. All right, I want to know, first of all, how much energy did the water gain? Okay, so this is our formula up here. Q equals mass times change in temperature times specific heat. Q energy is in joules. You can add this. Mass would be in grams. Energy, typically, S would be, if this is joules, all right, it would be joules per gram degree Celsius. And temperature change could either be, because temperature change in Kelvin or Celsius could be, they equal each other. So it doesn't matter which one you use. All right, let's run through this first option here of our math. Okay, let's solve how much energy the water gained from the block. The mass would be 125 times the heat of water, which is 4.18, times the change in temperature of the water, which was 4 degrees. And take a moment, calculate how much energy the water gained. Okay, I got 2,090 joules of energy. So a joule is not really all that big. 2,090 joules of energy. And that is the amount of energy dissipated to the block. So this guy's going to go here to the same. It's same, but it's opposite. This guy, the water gained 2,090 joules. This guy's going to lose 2,090 joules. So let's solve for this. Now let's solve for this guy right here. So in this case, energy, Q, equals mass times change in temperature times specific heat. I want to solve for this guy. So Q divided by mass times change in temperature equals specific heat. Okay, let's start plugging our values in here. Now again, keep in mind when I have my little table here, which is a pretty common table, I like this table. Each piece is just for an aspect of the variables here. Q is 2,090. The mass is 125. Change of temperature is 73. Now technically you have a negative temperature, but you also have a negative energy. So I don't always worry about the negatives because eventually your specific heat has to be positive. And that will do it. And you go ahead and calculate that out. Grab a color, give it a try. 0.22. All right, so 0.22. 0.22, that's joules per gram per degree Celsius. You could see a Kelvin here. That's really no big deal. All right, so that means that water has a heat of 4.18, and this particular metal is about 0.22 joules per gram degree Celsius. So that means that for 1 joule of energy per gram, this guy is going to raise up only a smidgen, but this is going to raise up a lot. It just takes very little energy to get this thing to raise up in temperature. So that means that for a low specific heat would mean a high increase in temperature per given mass per energy. All right, so in calories, how much energy needed to raise up? So you got two problems here. To pause the video, try them out. All right, so how much energy needed to raise 10 grams of water 1 degree? So it's going to be in calories. So now if we're in calories, that's an important piece here, because only time I really see calories used is in something like this where it's easy to do with some mental math. So Q equals mass times change in temperature times heat. So it's going to be 10 times 1 times 1. That's the specific heat of water in calories. So the answer is 10 calories. Figure it takes one calorie is 1 gram of water, 1 degree Celsius. So this is now 10 times that. How much energy would it take to do 10 grams? So it's going to be 10 times the one above, which is, well, think about it. Okay, if it takes, let's do it. Q equals mass times change in temperature times heat. Mass is 10, change of 10. This is 1, is 100. So we're doing this 10 times. You could do that without a calculator, likely. Okay, if you think about it. All right. A 25 gram block of aluminum, that's the specific heat, has a 1 or 2 joules of energy added to it. What is the final temperature of the block if it starts at 20? Okay, so there's 2 ways you can solve this problem. One, you could literally solve for TF, plug everything in, everything's provided, just solve for TF. Or you could solve for delta T, and then just apply that to your 20. It's going to go up from 20, so just take 20 and increase your delta T by that amount, because it's gaining energy, so it's going to get warmer. Okay, so let's solve this way out first here. So Q is, I'm going to go Q divided by mass divided by speed equals the change in temperature. That's going to be 150 divided by mass, which is 25, divided by 0.9 equals, okay, so we got 150 divided by 25 divided by 0.9 equals 6.6 degrees Celsius. So 6.6 degrees Celsius. So now if we start at 20, all right, plus 6.6 degrees is 26.6 degrees Celsius. This one, okay, and how do we do this? So it's Q equals mass times heat times, times the TF minus TI. But we have this little parenthesis here, so we divide out Q divided by mass divided by heat equals TF minus TI. Okay? That's one way to do it. And you could subtract it that way, or you could multiply together and distribute, but it looks a little bit issue here, so it's going to be this guy, and then this whole thing minus plus the TI, and that gets that guy going. Try it out. Look for 26.6. Now, one thing about this particular problem is you must be in Kelvin. So this is going to have to be 298, and you're solving for this, and it's going to be in Kelvin. So be aware of that. Try it out. You should, when you get your Kelvin, you should be able to subtract off the 273 and get us back into 26.6. Try it out. Make sure it works for you. All right. A 466 gram sample of water is heated from this to this. Calculate the heat energy absorbed. Go ahead. All right. So Q equals mass times change in temperature times heat. The mass is 466 times change in temperature. 74.6 6 minus 8.5 equals 66.1. So this is going to be 66.1, and this is 4.18. My answer will be in joules. If it shows to use 1 here, my answer will be in calories. A gold block of this block of gold, so water's here, gold is here. Same energy is applied to it. Previous question, what would be its final temperature if it's currently at 25? So now, let's go ahead and calculate that energy because we'll need it. 66.1 times 466 times 4.18, and we get a pretty good sized number, 128,000 kilojoules. So I got, in this thing, I got 128,754. 754 joules of energy. Now that's 6 sig figs. I would only want 3 here, so I can cut it off here if I'd like. Let's run it here. I got 100, and that would be equivalent to, let's say, 128 kilojoules, moving over 3 spots. So let's do that here. Take the same number. We'll use the same number. 128,754 joules equals, now Q equals mass times change in temperature times heat. What's my change? I'm going to solve the change in temperature. Mass is 466. Change in temperature times heat, which is 0.126, pretty low. Divide out, and what is the change in temperature? Change in temperature. So I'm going to divide by 466, divide by 0.126 equals 2,192 degrees. All right. So this is going to be 2,192 degrees. And of course, you would have to add 25 degrees onto this to get your final temperature. It's going to be really hot. Yeah, gold's got a relatively high melting point too, plus 25. That's going to be getting close. I'm sure we're getting quite close to its ending melting point, 2217 degrees Celsius. There's a good chance that we surpass the melting point on that one. All right, let's go to the next slide here. A couple of slides left, getting close to energy point. Okay, so here's another example. How we collect energy is called a calorimeter. So if I could take something that is hot or cold, for that matter, and drop it into this hole, and way down deep inside here, this thing radiates energy to the block. And the block starts absorbing all the energy. So a 500-gram block of aluminum, how much energy would it require to raise this thing 1 degree? We call this heat capacity. Heat capacity is the energy, joules or kilojoules, per degree Celsius. Think about that now. There's no mass in here. So for this particular object, it's not that the mass doesn't matter. For this calorimeter, if I take this thing out and drop in a new sample in, the mass never changes. So the mass on this particular substance here is never going to change. So it's a bit of a quick hit. It changes energy to your degree change in temperature. So it's joules per change in temperature. And it's a quicker little flip back and forth. If you're working in industry, you want to make something faster. Let's try it out. Q equals mass times change in temperature times heat. So in this case, this heat capacity is just a short version of this, where the temperature is 1 degree. And the mass is never going to change, which happens to be 500 for this item. And for this item, it's never going to change. So this item here will have its own heat capacity. Will that be the same heat capacity as something else? No. This particular, it's like a name. It's like a unique identifier. It's for this item. Okay. So it says 1 degree, and then the specific heat aluminum is 0.9. All right. So let's go ahead and calculate this. What would be the in this case, it would be 500 times 1 times 0.9 is 450. So it's going to be, the specific heat of this thing is 450 joules per degree Celsius. So every time this thing increases by 1 degree, 450 joules of energy must have been absorbed. So one of the more common questions is that you drop substance X into this thing and it raises 5.5 degrees. Okay? How much energy was released? That's where this comes in. Now it's a simple little conversion. It's 5.5 degrees, and we want to get rid of degrees, Celsius, and go to joules. 1 joule is 450 degrees, and therefore it's just 450 times 5.5, and that answer would be 2475 joules. 2475 joules. An example where this might play a role here would be, let's say, in a rotor. Now, your typical way in which brakes are stopping nowadays, well, we do have some newer versions where they try and reconvert the thermal energy, the energy of the car, back into the electricity. This is not like that. This is a typical just squeeze, use friction to stop a car. So this is called your rotor right here. This is on all of your cars, unless you got a new fancy car. The mass isn't changing. Okay. So how do I recognize heat capacity? Again, keep in mind it's energy per degree Celsius. When and why would I use heat capacity? Again, it's a simpler calculation for people in the industry. You might say, okay, how big does this rotor need to be? Now you can go to a bigger car, a fancy car that goes fast. Semi's huge. And then all of a sudden you go to a small little compact car and they're like little go-kart versions of this thing. It's tiny. It doesn't have to have that much energy. A car, small car, traveling has at the high speeds has way less kinetic energy than does a big one. So all this kinetic energy, okay, which is 1/2 mv squared, is going to be transferred into Q energy absorbed by that rotor, that metal rotor here, and it's going to raise up in temperature via Q equals mass times change in temperature times the heat, or heat capacity if you have that for the rotor. It melts around 1200 degrees. So you need to make sure this is large enough, even in the worst conditions of braking, that you wouldn't be able to travel, based on the mass of the car and the velocities that you're generally traveling, even at extremes. Now, where you might see this really have a problem is when you're up in a mountain and you're driving down a mountainside. That's a lot of potential energy, and all you're doing is brake, 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 and the brakes can get very hot. Okay. Either way, this is a great application of how we might use this particular idea of heat capacity or energy to know how big this thing is. I can double the mass of my rotor, and I would double the amount of energy that I can take into it without and have the same temperature change. Okay. And finally, we're coming down the end here. Again, keep in mind some of these deals here. Really watch your units. Okay. Energy per mole, energy per gram per Celsius, molar, some key terms. How much energy? Okay, remember with a heat capacity of this. I just did this. So I'm going to do it again. I did 5.5. You guys have here 4.5. Go ahead and try it out. If not, it makes sense. Go right ahead. Thank you very much.